Aloha. Today, artificial intelligence is a household name, powering search engines, voice assistants, self-driving cars, and even generating human-like conversations. The AI revolution, largely led by the United States, took off with the rise of deep learning and large language models developed by companies like OpenAI, Google, and Meta. But decades before ChatGPT or GPT-4 made headlines, Japan had already launched a bold and ambitious attempt to build intelligent machines. In the 1980s, during its peak as a global tech superpower, Japan announced a sweeping national initiative, the Fifth Generation Computer Systems (FGCS) project. At the time, the world took notice, and for good reason. Japan wasn't just excelling, it was dominating. Hitachi, Toshiba, Panasonic, JVC, Sharp, Sanyo, Sony, and many others had wiped out the US consumer electronics industry, flooding global markets with high-quality TVs, VCRs, cassette decks, and later CD players. Toyota, Honda, Nissan, Mazda, Subaru, Isuzu, and so on were overtaking Detroit automakers with reliable, fuel-efficient cars that appealed to oil-shocked consumers. In the photography market, brands like Nikon, Canon, Pentax, and Olympus surpassed traditional leaders like Leica in sales. But it didn't stop there. Japan wasn't content with just producing home electronics, cameras, and cars. The nation set its sights on leading the frontier of cutting-edge technology. In semiconductors, Japan surged ahead in DRAM, dynamic random access memory, production, outpacing US giants like Intel, Texas Instruments, and Motorola. Japanese firms like NEC, Fujitsu, and Toshiba produced cheaper, higher-yield memory chips that took over the global market, triggering serious alarm in Washington and leading to bilateral trade tensions and semiconductor protectionism. Japan also outperformed the US in several other strategic tech sectors. It became a global leader in industrial robots, battery technology, miniaturization and precision engineering, and even supercomputing. Japan's reputation for precision engineering and relentless innovation made it easy to believe that the next computing revolution, the fifth generation, would come not from Silicon Valley, but from Tokyo. The project was heralded as a game-changer, drawing intense interest, admiration, and eventually concern from the West. And yet, it quietly faded into obscurity. So, what exactly was the fifth-generation computing project? Why did it look like a precursor to modern AI? And what caused its failure, despite Japan's unparalleled momentum at the time? Launched in 1982 by Japan's Ministry of International Trade and Industry, MITI, and managed by the Institute for New Generation Computer Technology, ICOT, the Fifth Generation Computing, FGCS, project was a 10-year government-funded research program with a goal that was nothing short of transformative. The project aimed to create computers that could reason, understand language, process knowledge, and engage in intelligent dialogue. In other words, what we would now call artificial intelligence. The term fifth generation referred to a leap beyond the earlier eras of computing. First generation, vacuum tubes. Second generation, transistors. Third generation, integrated circuits. Fourth generation, microprocessors. Fifth generation, knowledge-based, intelligent computing. But unlike previous generations, which were defined by hardware, the fifth generation aimed to revolutionize the way computers thought and interacted with humans. The vision included natural language understanding, especially in Japanese, logic-based reasoning, machine learning, and even intelligent problem-solving, all in real time. The FGCS project wasn't just about building faster machines, it was about redefining computing itself. Its approach differed dramatically from both prior systems and from today's data-driven AI. At the heart of the project was a belief in symbolic AI, the idea that intelligence arises from manipulating symbols according to logical rules. The The chosen programming language was Prolog, a logic-based language ideal for representing knowledge as facts and rules. This rule-based approach aimed to mimic human-like reasoning. Instead of processing numbers, these machines would process concepts and relationships, allowing them to make inferences and solve problems based on structured knowledge. The FGCS systems were designed to work with explicitly structured knowledge, ontologies, semantic networks, production rules, and were intended to support expert systems that could make decisions in fields like medicine, law, and engineering. A major goal was enabling computers to understand and communicate in Japanese, which is an extremely complex language with flexible syntax and ambiguous writing systems. This focus on NLP prefigured modern AI's obsession with language understanding, albeit with vastly different tools. The project envisioned specialized hardware to support its high-level logic processing. It moved away from traditional von Neumann framework toward data flow and parallel architectures, such as the Parallel Inference Machine, PIM. The von Neumann architecture is the classic computer design model that underpins most traditional computing systems. It's structured around the following core components: input, memory, CPU, and output. For more information about the von Neumann architecture, please view my video titled John von Neumann, Architect of Computing and Visionary of AI, which is available in this channel. A central goal of FGCS was to overcome the limitations of the sequential processing inherent in the von Neumann architecture, often referred to as the von Neumann bottleneck, which was seen as unsuitable for the massive parallelism required for artificial intelligence tasks like inference and knowledge processing. The new framework was designed to speed up logical inference and better handle the simultaneous evaluation of rules, essential for Prolog-style computing. Instead of specifying how to compute something step by step, a Prolog program consists of a collection of facts and rules, forming a knowledge base. While it didn't use neural networks or massive datasets like modern AI, FGCS was absolutely aiming for intelligent behavior. It focused on understanding language, performing inference, learning new knowledge, and solving problems autonomously. In that sense, it was an early form of AI. However, it was firmly planted in the symbolic, rule-based AI camp, as opposed to the statistical, pattern-learning AI that now dominates. Why did it fail? Despite the hype, funding, and global attention, FGCS never lived up to its expectations. There were several key reasons. The first problem is its over-reliance on symbolic AI. The project's core assumption, that logic-based symbolic reasoning could scale to real-world intelligence, turned out to be flawed. Symbolic systems struggled with ambiguity and nuance, incomplete or noisy data, and learning from experience. Meanwhile, statistical approaches and neural networks, which FGCS largely ignored, began showing promise in tasks like speech and image recognition. Second, the advanced PIM hardware never delivered a performance edge big enough to justify abandoning conventional CPUs. Moreover, writing efficient parallel logic programs was extremely difficult. Another factor is weak software ecosystem. Prolog remained niche, and developing large, robust applications in it proved cumbersome. Unlike C or later Java, Python ecosystems, there wasn't a vibrant developer base or library support. The FGCS project also got caught in the broader AI winter of the late 1980s. Disillusionment with symbolic AI set in globally, funding for AI dried up, and optimism about expert systems faded. FGCS formally shut down in 1992, without achieving any of its headline goals. The fifth-generation computer systems project was one of the boldest technological efforts of the 20th century, a moonshot for artificial intelligence before the term was even mainstream. It sought to build machines that could reason, understand, and interact like humans. Japan, at the height of its industrial and technological dominance, seemed destined to lead the world into this new era. But while the vision was compelling, the underlying technology couldn't deliver. Symbolic AI proved too brittle, custom hardware underwhelmed, and the software ecosystem never took off. FGCS became a cautionary tale, brilliant ambition, but flawed assumptions. While the FGCS project fell short of its grand goal to usher in an era of intelligent, logic-driven machines, it was far from a wasted effort. FGCS helped the world understand that purely rule-based AI doesn't scale well in messy, real-world domains. This was a major reason why, when deep learning started to deliver real results in the 2010s, researchers were more willing to adopt a data-driven mindset. Ironically, the knowledge representation and reasoning goals of FGCS are being revisited today, now combined with neural models in fields like neuro-symbolic AI, knowledge graphs, and explainable AI. The project showed that designing exotic, specialized architectures only works if you also have a compelling software ecosystem and developer community. Despite its commercial failure, FGCS showed the world what a nation could attempt with centralized, long-term, publicly funded research. It inspired international responses. For example, the U.S. Strategic Computing Initiative was launched in direct response, whereas Europe kicked off a spree focused on AI and information tech. The FGCS project put AI on the geopolitical map, decades before it became today's economic and strategic battleground. And now, in an era where AI once again dominates global attention, we're seeing a new appreciation for some of the very things FGCS championed: explainability, symbolic reasoning, structured knowledge, multimodal interaction. Only now, we're blending them with deep learning and massive data. In a way, FGCS may have just been too early. Was the fifth-generation computer project a massive misstep, or did it offer valuable lessons despite the outcome? Do you think Japan could have been a global AI leader today if they had taken a different approach? If Japanese scientists and engineers had embraced connectionism, the foundation of neural networks, instead of the symbolic approach to AI, could they have been the first to develop large language models? I'd love to hear your thoughts. Please drop your comments below. If you found this video helpful, don't forget to like, share, and subscribe. Mahalo.